This video brought to you by Lego Mandalorian. So we just said in the last video that the natural log, this ln x, was actually log base e. That's how we interpret it. So this is how you would see it written. And recall we also said that log of some value was log base 10. So we're going to smash these in our calculators, and you know me, I much prefer the good old-fashioned Desmos calculator. So here we go, just typing them in. So I'm typing in ln of 645,778, and my value is approximately 13.3782. And then I'm typing in log, and Desmos is programmed to read them this way. So this is negative 4.622 if I round it to 3 decimal places. I don't have to type this one in. I know it's undefined, because the a value, or whatever we evaluate log of, has to be positive. That's what we noted in the definition of logarithm. Okay, so we're doing now log of 778. So I'm just going to type this one here, and that is 5.81000. Natural log of 1, that's got to be 0, but let's double check it. Who knows? I could be wrong. Yay. And then natural log of e, that's got to be 1 because the bases match. But let's just make sure you see how to type that in. I just hit E on my keyboard for Desmos, and it smashes it right out. So here's what I wrote down for each of those. Not a big deal here. Just make sure you know how to type these things in Desmos or your TI 83, 84 calculators. So if you're doing them in there, you would just type, here's your ln button and here's your log button, and just type in your stuff. This formula used to be super useful. If you use the helps in MyMathLab, they actually have you using this formula. It was partly because the TI-80 series or these calculators didn't used to be able to do change of base formulas. Same thing with Desmos, but I'm going to show you how to use Desmos to do the change of base formula. So essentially, you can rewrite a logarithm by picking a new base in any base you want. So because your calculators were used to be programmed just to have natural log or common log, you would use log base 10, or you would use natural log. And way back in the day, before calculators were super popular, engineers had massive books that were just a ton of different logarithms because it was so tedious to do it by hand. So let me show you this in Desmos. What I want you to see is that all three of those were the same thing. So log 8 divided by log 5, 1.29, blah, blah, blah. Natural log 8 divided by natural log 5. Oh, same thing. And then Desmos, if we go into the keyboard, hit the functions, and let's see, I believe it's under miscellaneous. Here it is, this log A button. We can now put in the log. Remember, it was log base 5 of 8. All of them give us the exact same answer. These are all acceptable ways to approximate a logarithm. So 1.292. Isn't this exciting? Oh my goodness, I hit record. Okay, so here's the graph of logarithms of several different bases. Our goal is to figure out what happens when we rewrite the equation to be this: y equals some number a times log base b of x minus h plus k. Ooh, right? We already know all of these things. So we need to know, how does A affect the graph? Well, it's going to be a stretch or compress. How does B affect the graph? It's going to be a stretch or compress. How does H and K affect the graph? It's going to be blah, blah, blah. So take some time with this video or this bit.ly link to verify these things. And then I'm just going to real quick smash these out. So natural log is, let's see, I believe it is this one right here. No, this is log base 10, because note that when we do log of 10, that should equal 1, and that's what's corresponding here. And then this is the natural log one here, because when we do natural log of e, we get e, and recall that e, oh, you can't even see what I'm writing. E is approximately 2.71, blah, 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 blah. So that's a value between 2 and 3 here. So when we get down here, I'm just going to take this graph and I'm going to remind myself, what does the +3 do? Well, it is a shift in the negative direction 3 units. So I would go here, and it turns out that this -3 ends up being a vertical asymptote, and the new value here, -2, is when we'd get a natural log of 1. And so my graph is going to look, I don't know, something like that. This is x equals -3. Oh, this one's really hard to show because it's multiplying by 3. I guess it's not that hard. Note that we have the same vertical asymptote of x equals 0 of the most basic graph, but then instead of crossing the x-axis at 3, we're now at 1, we're now crossing it at 3. So, yeah, you get the idea, right? And then here, oh boy, okay, this one's exciting. What are we doing here? We're going to shift it 4 units to the right because of that -4. This becomes the new vertical asymptote. 5 is where we would have been at 1, but we're going to multiply it by a half. So it would be 4.5 is where it crosses the x-axis, and there's our rough shape. If you want exact shapes, just jump into Desmos and smash this in there. I'm hoping you've seen the idea of what does the AH and K and all of that do. Okay, last one. Here we're going to shift it all up 1, but since the range is all real numbers, shifting up 1 doesn't really do a whole lot. And then that 1/3, that's going to be a stretch thing. You know what? On this one, I'm going to smash this in Desmos. So let's do that. I'll type in the whole thing. P of x equals -2 natural log of x divided by 3 plus 1. And so you can see that the -2 flipped it across the x-axis, and then we're crossing at 4.946 instead of 1. So the shifting up of 1 changed this x-axis value, and so did that 1/3. I feel like we should take the time to figure out all those exacts, but maybe ask me to do that live in class. Okay, so there's our stuff, 4.964.